Hello, welcome to another control lecture. So in this short video, we're going to look at the modelling of a feedback control system with focus on PID control. In this case, it's got a PI, and we'll look at the following operational considerations, so the practical consideration. So measurement noise and transport delay or delay, sampling interval, we'll talk about briefly, disturbances due to the chain mass, and also the actuator saturation and anti-wind-up. So in terms of the measurement noise, you'll see here in the feedback, and what you'll see is I've added this block here. So I've got this band limited white noise that you can find in sources, and I'll talk you through that in a little while more when we look at the Simulink model. And I've also added this block here for a delay, so we can effectively encounter for the delay from the measurement, although the value that in there is very, very small that we've selected. Sample interval, so we'll select sample interval in the PI control, the 0 to hold, and also the blocks for down here. Disturbance is due to the chain mass. This is quite interesting because as the climber, we look at the operation of the climber, as it's climbing up the pipe, you'll see there's a little offset in terms of the chain mass, and then you'll see that the chain mass, as you would expect, is increasing and decreasing as the pipe climber climbs and descends from the pipe. So you see that initial offset, and you see here the mass of the chain is increasing, and the mass of the chain is 0.17 kilograms per meter. So how we've gone about modelling this is, what we've got out here is the displacement, because we've modelled here the motor using a first order transfer function, so the actuator, and the process here using a second order, and what we've got coming out of here is displacement. So as displacement, obviously the climb is going to increase displacement and decrease displacement because the reference that's put into the model is given by this here. So you can see where this here corresponds to 1.8 meters and then 0.8 meters. So effectively our first reference is 0.8 meters and then down to then 0.9, back down to the bottom, midpoint, top, bottom, and then midpoint, and you can see it holds for that 5-second period in the middle. So that's our reference, so it's distance, and what we're getting at here is distance, or displacement we could say. So what we do is we've got this here, this summing junction, we account for the 0.4 meter offset in terms of the chain mass, and then we're multiplying the displacement here by this constant gain MC, where this is effectively the chain mass, so 0.17 kilograms per meter. That's what we define as the system gain there. And then that is then into this summing junction we've got a negative value. And you can see here in terms of the system output here, you can see if you're looking at this, so you can see that's your reference, you can see the disturbance here in the orange, so you can see it's increasing, decreasing, and then decreasing back to obviously where it started as it kind of climbs and then descends the pipe, and then you can see here the disturbance that it's having on the system. And you can see here actual displacement and measured output, they're pretty much on top of each other, but the actual the measured output is over the actual displacement, and there's a little bit of noise on that, but we'll run that in a little bit so you can see it a bit better. So that is accounting there for the disturbance due to the chain mass. So initially 0.4 offset, and then multiplying by this, so as the displacement increases, multiplying by this gain to count the mass of the chain changing per meter. This is obviously the disturbance is going to increase and decrease. And you can see here I've put a 0 to hold. That's found in discrete in Simulink library browser, and then the transport delay is found in continuous. If you're unsure about some of the components here, watch the previous video and in this series, and it'll make a little bit more sense. So what you can see now here is the Simulink diagram, and if we just going to move this slightly. So if you look at this, and then you've got the MATLAB script here that we're using to effectively define the parameters in the model. So in terms of the noise here, so the bandwidth limited noise, if you double click on this, you'll see here, what I've done is I've defined here noise power as N, sample time as TS t subscript s because it's defined here. So at the moment n is given by this quite a small value. So let's run the simulation and then see what graphical output we get. So if you're looking at this at the moment, you can see here there's a little bit of noise on there. You can see, so what we can do is we can increase the noise, so let's reduce it by a factor of 10, rerun it. And there you can see the noise has been, there's a little bit of measurement noise on the signal here. A bit more than previous. We'll change it back to normal. What we can do is we could put a filter here to affect a low pass filter, and we'll talk about that a little bit more in future videos. In terms of the sample interval, you'll see that I've defined the sample interval in the PID block. So if you look at the previous video, so a bit more detail with this, you can see t subscript s. You can see at the moment I've tuned it and I've got a PI, so I'm only using the integrator method, and in this case I'm using the trapezoidal method. And I've also defined the TS in here. In terms of the chain mass, we can, if we were to increase maybe the chain mass, so let's increase it significantly and then rerun the simulation, and you'll see that the climber now you've got this introduce this disturbance here. So maybe you need to go about retuning your PI controller or maybe a PID controller. So you can see in terms of that now, the control's not working that effectively given that disturbance. It might be due to maybe the saturation and the anti-wind-up that's added. So introduce the saturation block here, so it effectively limits the output, well in this case the upper limit from the actuation, and you can see I've just given it a value of 2.2. In terms of a transport delay here, let's just call it a delay, I've introduced a delay here and I've put a very small value, 0.02, and if we were maybe to put a 1 second delay, I don't know, you might get a huge delay for some reason, very unlikely with this application, but you'll see that the system now is giving you something that's pretty undesirable, and it'd probably end up with a system that perhaps would go unstable or fail. And the same would go if we were to introduce a kind of a sample interval, so from 0.01 to now 1. You'll see that the system now is again not, as you just saw, not behaving desirably. Okay, we're sampling too slow. Not enough information is being provided to the controller on a regular basis. Well, information is not being provided to the controller on a regular basis, and it's likely the climber would just hit the top. It would, just wouldn't get desirable control. So hopefully you found this video useful and kind of introduce you to the idea of some of the practical considerations and how you can model these within using MATLAB and Simulink. So if you've got any questions, please email me. Thank you.